Welcome again, everyone. It's a great pleasure here to be able to talk a little bit about some of the aspects of the work we're doing in my research group. And I'll talk about today about the focus on the value of data and hydrological modeling, linking very nicely to what was just said about how important the data actually is. But it's also important to think about what data is really how important. To give you a quick overview of what I'm going to talk about here is I'm going to start with a short, I should say very short introduction to the Hpv model, which is one hydrological model that has been used a lot, not only in our group, but also in general in many different groups. And it's kind of the idea is to give some kind of common understanding what a simple hydrological model could look like, to make that, when we go through the week and talk about modeling, have it more as one concrete example of a model. Most of these simple models, they don't vary too much. I mean, it's basically similar ideas, whether it's the Hpv model or any other similar type of model. I will talk about why we should use these simple models at all, comparing to more physically based models. We'll talk about benchmarks and how important those are for quantifying or evaluating how good our models of different complexities are. And that leads on to the value of data, the question of what do we really need to know if we want to calibrate our models, which type of information is most useful. And I'll end using this value of data approach in a citizen science project which we're currently running in Zurich. And where one of the questions is, what value can that be? If we collect data in non-traditional ways, how useful could such data be? So let's start with this very short introduction of the Hpv model, and I tried here to squeeze together what I usually give in 2 to 3 hours introduction to make that as kind of condense it, running it quickly through here, just to give you an impression of a typical bucket type model or conceptual model, as they're also called, how that works. Linking to we have heard previous today about the historic aspects, and here's kind of, I want to add some kind of historical perspective to that with respect to the Hpv model. Here you see Sten Bergström, which is the father of the Hpv model, and you see him twice. On one side, how he looks approximately now or a few years back, and then how he looked while doing his PhD, which was developing the Hpv model in the 70s. And it's not only Sten Bergström aging a little bit, but it's also, if you look in the surroundings of his working place, it's kind of important to remember these type of things when talking about the development of hydrological models. You can see the calculator there in the background, which is quite a large thing and probably was not by far not as powerful as any type of smaller calculator we have today. You can see the phone, which is also that is looks more like in a museum than the iPhone we have today. But most important for the hydrological modeling, if you see the paper, that were printouts. At that time, you couldn't just print the simulated graphs on the screen, but you had to print them on paper out, and then Sten is telling up the stories about how they were crawling over the ground to see different events and to pinpoint those and discuss different model failures or where the model was good. So this is just to kind of remind all of us that computational power and plotting possibilities have changed quite significantly during the past, 40 years. And so that's kind of, from the beginning, there was kind of much more limitations into hydrological modeling than it's now. And that also explains why in the beginning, in the 70s, was quite much to do. A lot of things which you easily can do today took much more time. I myself started modeling in the late 90s. At that time, one of the Hpv models still took a minute or so. Now it's less than a second. So this kind of these computation times also mean that you can do more ones or more detailed ones. Okay, so another historical aspect with the Hpv model is here you see the first simulation that was done with the Hpv model. It was a small catchment in central Sweden, Lilla Tivsjön, and you see the hydrograph for a few months. And the fit was surprisingly well, and it was, at that time, it was a great achievement to have this kind of simple model and get something out of that. That was about me at the same time. So again, kind of showing some kind of change. Things have changed in the past years. This was the catchment, the gauge that was used to measure the data used in these first simulations. Visited that 15 years back. By now, it probably looks even less working. At the time, wasn't really working. But the Hpv model is still being used, and it's still being used despite the fact that when I started my PhD, or working with my PhD in the late 90s, people told me, well, you're working with the Hpv model, but that won't be used much more. Because at that time still there was a thinking, oh yeah, with more computational power, we can go to more complex models. As it turned out in the past years, it was more, these simple models still around, still are very frequently used, and actually people more and more realize that it's the data limitations rather than the model computational limitations that is still a good argument to use simple models. We just often don't have the data which would be needed to run more complex models. Here's a summary of what a few statements about the Hpv model. As I told you, it was developed by Sten Bergström as SMHI, the Swedish Meteorological and Hydrological Institute, as part of his PhD. It's a very simple model. It's basically a lumped model. They put together things, but you can divide your catchment into elevation zones, which is very important, of course, in catchments which have elevation differences. You can also divide different land use classes if you want. You can divide different sub-catchments. But basically, it's a model that is lumping together things. It's very easy to learn and understand, relatively easy. So hopefully, by the end of today, you have a good knowledge about the model, or at least some understanding, and you are able to run the model. And this is even these days a big advantage to more complex models. Very oftentimes have a rather steep learning curve that you have to invest quite some time, weeks, months, before you really learn the model and know how to run it. The Hpv model has been developed in Sweden, but has then, since then, been applied in a lot of catchments, not only in Sweden, Scandinavia, Europe, but also worldwide. And most of the time it gave good results. And then, of course, we can discuss what it means, good results. But somehow it seems to produce something that people find useful, even for catchments outside of Sweden, even for catchments which never was intended to be used from the beginning. So which means it's a quite flexible model that can be used in a lot of different climate zones. One of the nice things with the Hpv model is that it requires relatively limited amount of data. So you need precipitation, temperature, and if you want to calibrate the model, runoff. So and then some estimate of long-term evaporation. So this is basically the minimum requirement you can have for a hydrological model if you want to model anything. And that is kind of being able to go with little data is, of course, something that means that you can apply it in many places. The Hpv model can be run on any PC or any computer. And I still have this 286 or better here in my slides, which is kind of from my very first lecture about the Hpv model. I guess most of you don't know what a 286 is. I have to look to Dimitri, and some of you remember certainly the silly days. 286 was the first processor on the PCs which you had on your desktop. And that was a huge difference to be able to run your model on your own desktop rather than go into some computational center. to run the model. So at that time when I started, I could run the Hpv model on my computer. For the She model, which we'll talk later about, a more complex model, I had to go to a computer center, which partly might explain why I'm stuck to the Hpv model. It was much easier to run it. Because it's so simple, you have many different versions. There's this original Swedish version, there are different versions there, a Norwegian version, a Finnish version. We have in Switzerland our own version. Francesca told me she has her own version programmed in R. There are many different versions, and it's very simple, easy to program. For those of you who are into programming, it's about 2 pages of code is the core of the Hpv model. Then there's a lot of things, of course, around data input, output, and you can do things more complicated. But the core modeling code is about 2 pages, so really not very long. And yeah, one thing, I'm not sure whether you can see it down there. I always get this question, Hpv, what does it stand for? Whenever I write a paper, some reviewer wants to know that. So Hpv stands for Hydrological Byråns vattenavdelning, which is was a unit of the SMHI at the time the model was developed. SMHI has been reorganized several times, and the unit doesn't exist anymore, but the name Hpv kept. But it doesn't really say anything other than the unit where it was developed. As we heard previously, we can distinguish models into different classes, and these are kind of here the 2 main classes. On the one hand, the conceptual models or bucket type models, on the other hand, the physically based or distributed models. So the bucket type, where we put things together and we don't really exactly follow each water drop to the catchment, but have a more conceptual idea how things work. So, which is kind of, when we go through the Hpv model, you can see different examples of how this conceptual thinking. And then on the other hand, it's the physically based, fully distributed models where you really can follow a water drop to the catchment, and you can really say, well, if I change a tree here, how does it influence runoff? And the models are useful for different tasks, and but it's kind of, then there's of course oftentimes also kind of in between things, but it's important to have this kind of, to remember these 2 different types of models, which also means when it comes to calibration and model parameter uncertainty, with the bucket type models, we often have typically 5 to 20 parameters. With the physically based distributed models, we end up with hundreds of parameters. So there's a kind of very, very large difference. Okay, so what do we need to run a model? The Hpv model, and basically any kind of bucket type model, requires some kind of basic information. So that's the aerial precipitation, so the precipitation over your catchment, the temperature, and then we need also the potential evaporation. For precipitation and temperature, there are variations with elevation. So usually precipitation tends to increase with elevation, at least up to a certain level, and typically around 5 to 10% per 100 meter. For temperature, there's a decrease of temperature with elevation. And that, of course, makes it very important to consider elevation zones if we are simulating high mountain areas. Because in high mountain areas, you might have, for instance, you might have snowfall in the higher elevations and rainfall in the lower elevations. Or snowmelt always starts in the lower elevation, but it's still snow exists in the higher elevations. And that's kind of a very important thing to consider. Potential evaporation is also needed. There, for the Hpv model and similar models, it's oftentimes enough with very kind of long-term mean values. So that's what we call the 12 values. So it's a long-term mean monthly value. And those can be then calculated by some more physical equation, a Penman formula, or can be by basic measurements. Usually the model is not so very sensitive to these formulations, because there's some way of compensating. So if you overestimate your potential evaporation, then the model will be calibrated so to restrict the evaporation more. There is one simple modification in the Hpv model with this potential evaporation, the long-term values. That is that we correct the potential evaporation for temperature anomalies. And that's typically for this type of models done very pragmatically. So the people at SMHI, they realize, well, sometimes during the cold summers there's less evaporation, but then during dry summers it's more evaporation, or to hot summers. So they introduce this correction of the using temperature anomalies. If it's warmer, then it should, normally during summer months you have more evaporation. If it's colder, you have less evaporation, and to correct that. I can also share the lecture later as PDF, so if you want to have slides, I have them as a PDF and can send that to Tatjana, and then she can distribute it to everyone. Okay, so now we have the input. Now we need to go through the model, and basically these type of models are built up in different routines or different compartments, which then can be exchanged also. The typical is you have a snow routine, which takes the snow and precipitation in, calculates the snowpack. The output is a snowmelt, and the snowmelt together with the rainfall goes into the soil zone. In the soil zone or soil box, you calculate the evaporation that goes to the atmosphere, and the rest goes as groundwater recharge, going to the groundwater. Then there's a groundwater box, and in the end, some routing along the stream, and then it goes to runoff. So conceptual model means we don't really use it physics or physical equation, and that's a very good example is a snow routine. We know the physics of snowmelt pretty well. We know the energy, we could come up with the energy balance, we know how much energy is needed to melt a certain amount of snow and so on. But usually we don't have enough data to run physically based energy balance models for snowmelt. So rather we use a very simple approach called degrade approach, where the melt is calculated by a factor times the difference of the temperature with some threshold temperature. Threshold temperatures, of course, usually around 0 degree. And that means if you have a certain amount of plus degrees, then you can melt a certain amount of snow. This degrade method works so well because temperature is also dependent on radiation. So radiation, or the incoming energy, is driving the snow melt. At the same time, incoming energy is heating the air. So heating the air temperature, therefore, is a measure of how much energy there is for snow melt. And it has been shown that this degrade method works at least as good as physically based physics equations as a catchment scale in most applications. Isolated against the cold, so it needs to be much colder for a longer time to kind of refreeze this water again. So this process is slower. Therefore, we have a refreezing coefficient, which usually is set to 0.05, which means the refreezing is 20 times less efficient than melting. A very important parameter, which is kind of a little bit hidden sometimes in the description, is the snowfall correction factor, which compensates for two things. It compensates for the the measurement errors we do during snowfall. As you know, oftentimes the snowflakes, they want to go everywhere, but not in our gauge because of wind turbulences. So there's a large undercatch of snow, which then would mean that the snow correction factor should be larger than 1 to compensate for the measurement error. On the other hand, in the Hpv model, there is no sublimation from the snowpack. So the snowfall correction factor also takes part of that, so snow leaving the catchment into the atmosphere rather than being melted later on. And that that's then causing oftentimes the snowfall correction factor to be smaller than 1. And that's a very important parameter if you want to get your spring flood right, because the threshold temperature and this degree day factor, they will shift things in time and shift it in the speed of the melt, but they would just shift things in time differently. Whereas with the snowfall correction factor, you can change the volume of your spring flood. And importantly, all these calculations are done for each different elevation zone. As I said before, you can have snow melt ongoing on the lower elevations, but still snowfall in the higher elevations. Okay, so that was the snow routine. Now then water comes into the soil. The soil routine is probably that which differs most from other type of models, and this where Steen-Bergström was most creative in defining a function here. So in the soil routine, we have to decide of how much water stays in the soil and then potentially goes to evaporation at some point, and how much goes on to groundwater. And you could have a simple idea of a bucket. You fill a bucket, you have a bucket, you fill it, and first when it's filled, then it spills over, and then it's going to the groundwater. That would be the idea of you have your maximum capacity in the soil, you have here the soil moisture, and then if you look on the fraction of the rain and snowmelt that goes down to groundwater, in a bucket that would be a straight line. Once you filled it, everything would go up. So very steep here. And but then in nature, things are usually not working that on-off, at least not on the catchment scale where things average out. You have thicker soils, thinner soils, so things vary over a catchment. And that's why this beta function was introduced, which defines the fraction of rainfall or snowmelt going on to groundwater as a function of the soil moisture status. So if you have going here from no water in the soil to the maximum capacity, if you have no water in the soil, then of course anything coming in should stay in the soil. So this point is very given. If you are here, this point, if your soil is filled, then everything should go down to the groundwater. So this point here is given. And then in between, you need some kind of function. And instead of having the step function, now it's this function where the ratio times to a power is calculated. So this is an example for power 2. If you have power 1, it would be a straight line. For 4, it would be a bit more curved. And for 10, it would be almost like this bucket model. This is a good example for a conceptual model. There are some concepts. So if there's no water, then something should happen. So you have some conceptual understanding, but it's not really physical values. This parameter Fc sounds like field capacity, and that's because sometimes, for historic reason, it was called like this. But be aware that this is not the field capacity you would measure if you go out into the field. So all of these parameters in the Hpv model are kind of effective parameter at the catchment scale, which can't be measured directly, but can be derived through calibration or regionalization. Okay, so now we know how much water is going down to groundwater. We also need to kind of calculate evaporation. Again, conceptual thinking. If we have here the soil moisture in the soil box at a point in time, if you have no water in the soil box, then evaporation should be 0. So your ratio between the actual and the potential evaporation should be 0. Of course, there's no water, nothing can evaporate. On the other hand, if your soil box is filled to capacity, there's no limitation for water to evaporate, so you should have this value of 1. Everything you have evaporation equal to the potential rate. And now, again, you have to do something in between, and the reasoning here is to say, well, up to a certain degree, even if the soil is not filled to capacity, it's almost filled to capacity, so the limitation on evaporation is not that big, so let's still assume everything is evaporating, that only can. But then after some limiting factor, you decrease, and then here it's chosen to have it linearly. Of course, as always in this type of models, you could have chosen many different versions, different formulations, There's a good argument to make it this way, but you could have also used some kind of exponent or something here. So important then comes this function controls the evaporation. The function before controls how much water is staying in the soil box to start with. And if we summarize that, or look at that, how the effect of different parameters. So we can think of, if we have FC, so the size of the soil box, if that is larger, there's a larger potential to store water. That means more can evaporate, which means runoff will be smaller. Same is true for, if beta is larger, that will be more curved. That means for each individual soil moisture status, you will have more water staying in the soil rather than going to runoff. Again, evaporation will go up and runoff will go down. And then for LP, it's the other way around. If LP gets smaller, this point is shifted towards here. That means you have a larger evaporation and again, runoff going down. So all three parameters influence the evaporation and influence by that also indirectly the amount of runoff. And then you can say, well, if all three do the same thing, why care? Well, the timing and exactly when these different parameters work, that differs quite a lot. So about here as an example, just this curve where we run the model once with a value of 150 and once with 200. And you see the difference here mainly during the re-wetting after summer. So during summer months, being here, your soil box gets dry, and then during the re-wetting, with a larger value of FC, it takes longer time to fill the soil box again, so runoff is smaller during that time. Whereas if you change the value of beta to a larger value, the effect is more seen already earlier during the summer season, when you have dry soil and you have a certain number of rainfall events, and depending on the value of beta, more water makes it to the groundwater or not. So if we just go back and forth, you see that the shift is in different parts of the season. So that's why these different parameters, even if they all control operation, they have slightly different consequences for the simulations. Okay, quickly continuing to run through the model. Now we are follow the water, we are now in the groundwater. The typical setup in the groundwater box is like this here, where we have two boxes, an upper groundwater box representing shallow groundwater, a lower box representing deeper groundwater, actually also representing any lakes that you might have in the catchments. But basically it's two boxes. The boxes have linear outflows. The upper box has two outflows. Altogether, this becomes then non-linear, and there's some thresholds, like this threshold U theta L, which means that once we have reached that level, then also this outflow kicks in. We have the value PERC, which just means how much water can be transferred from the upper box to the lower box per time step. So maybe 3 millimeters per day. So 3 millimeters from up here drain down. That means, on the other hand, you need to have an input of more than 3 millimeters to start building up groundwater levels up here. And once you build up here, this outflow kicks in, and then if it goes to continue rising, you have this upper outflow here. So 3 different outflows, each of them linear, but in the combination, that makes a non-linear relationship between water storage and outflow, with more water flowing out if the storage is higher, and it's more than linear increase. These different outflows are then combined, the different boxes are combined into one runoff, and now only the last step remains, namely the routing routine. So we need to get the water from the different parts in the catchment to the catchment outlet. And here we use a very simple model approach with just one model parameter called max bars, which is a length over the time over which we distribute the water at the outlet. And that's then a triangular function where we assign weights to the different dates. So in this example, if you say it takes 5 days for all the water coming to the outlet, that means that 10% of the water comes today, 20% tomorrow, 25%, 40% the day after tomorrow, and so on. Or if we turn around, if we think ourselves standing at the outlet and look what water is coming across, this water, what we're seeing at the outlet today, is an average of today's simulated runoff to the stream network, some of yesterday's, some of the day before yesterday, and so on, back in the time. And the effect of this routing routine is this transformation here. So the hydrograph is dampened a little bit and it's shifted a bit in time. So that's exactly what we want to have from a routing, dampening and shifted in time. Okay, so that was the very quick run through the Hpv model. I've gone through the snow routine, the soil routine, and then the groundwater routine, and in the end this routing routine. So to come from rain and snow input temperature coming out all the way to its computed runoff. So what is missing in the Hpv model? Basic, yeah, well, that's kind of, we simulate, in the Hpv model we always simulate everything in millimeters per time step, so in specific values, so we don't, it's the calculation from the runoff height is already done. But there's one process totally missing. Well, there are several processes, but one important. Transpiration, yeah. So, in general, these things there are missing. I talked about the soil, but I never said anything about vegetation. So we have transpiration, and interception is not included. These trees, the model has been developed in Sweden, which is known as a rather tree country with some trees. Why does the model work without trees? Shouldn't that be totally wrong? Well, apparently not. It has been used quite a lot in forested catchments. So which process is taking part here? Yeah. Well, evaporation is calculated in the soil, what I described as a soil routine or soil box. Actually, to be correct, that soil box should be called soil vegetation box, because it's taking care of all the evaporation fluxes and also the transpiration. And that's a good example of this type of conceptual models where you describe something, you give parameters names, you give your routines names, but you have to be careful what they really mean. So what the soil box in the Hpv model actually should be called, to be correct, it should be called soil vegetation box, because it somehow takes care of all of that. There have been versions of the Hpv model where interception, for instance, was simulated outside of the soil box explicitly. It turns out that parameters are then so much linked to the soil parameters that things are compensating each other, and you don't get any better model results by including an interception routine. So it's not worth including the trees to get better runoff simulations, because they are already considered implicitly in the soil box. Okay, when we calibrate the Hpv model, from the beginning this was trial and error calibration. Of course, that is very time consuming, so people have then developed automatic calibration routines. Still, it's quite useful to calibrate the Hpv model manually by hand in order to learn the different interaction of different parameters. That's what we're going to do this afternoon, to kind of get a feeling for learning the model. But then automatic calibration can be useful if you want to do it in many catchments and repeat it. There are different criteria. Of course, you can visually say, oh, this looks good, this does not look so good. Of course, then on the other hand, you want to have something which is more objective. And the most commonly used statistics in the past years is this model efficiency or Nash-Sutcliffe criteria, where you compare compare the squared model errors by some benchmark, which is in this case a benchmark of, you assume you have constant runoff all the time, and then you calculate the ratio here. Basically, it's a way to scale your quadratic errors by the quadratic errors which we would do if we would assume that it's constant runoff all the time. We come back to that. So I talked before about this kind of different types of models. And now I've given an example of a typical conceptual model of this Hpv model. So why should we use a model like this and not a more complex model? And just to make a case here, the common complex models like the model, hydrogeosphere models, they really follow all the physics and you follow all the water drops. I can skip that. So the kind of argument why still bucket type models have their value is that if you think of more physically based models, they also have a resolution of several hundred meters often. If you look in reality, you have roots, you have rocks, you have all that kind of thing. So even if you have more detailed scale, it's still basically each grid cell is more or less a conceptual model because you don't have the real parameter values. It's very hard to measure them, measure hydraulic conductivity at a scale of, is determined for a scale of 50 or 100 meters. To give another example here, a small irrigation experiment we did in Switzerland, and you see how heterogeneous the soil is. Some cracks, water flows into there. That is this kind of level of detail, even in the most high resolution physically based models, it's hard to get those. And Stein's argument for simple models is this nice airplane analogy, asking then the question, well, of these two models, which of the two looks more realistic? And which is closer to reality? And, well, coming here on the Swiss flight, I would say actually the one on the left side looks much more like the plane I was actually flying in. But then when it comes to the question which of the two models would fly, I would guess much more on the right-hand thing, which is a simplification of the real airplane, but opposite to the kind of close to the reality model, this one actually will probably fly at least a little bit. And then that's kind of to the kind of nice analogy Sten Bergström often was doing in terms of kind of his argument why we sometimes need to simplify to capture the characteristic features of a system, here the airplanes, but in our case the catchment. So basically, essentially all models are wrong, more simple and more detailed, but some can be quite useful tools if used correctly and if you're aware of the limitations. And one way to kind of use models as a tool is, there's an example here, if you want to have a land use change and we want to detect changes, we can, for the detection, we can very well use these very simple models. Because then we just use the model to reproduce the runoff which would have been observed if there wouldn't have been a change. So we calibrate it, and then we run our model after a land use change. We observe some runoff which has been influenced by the land use change, and we can use this comparison to quantify land use change effects. And just two examples from catchment in the US. There was a clear cut in one case, there was a wildfire in the other case, and by looking on the deviations between the simulated runoff and the observed runoff, you can clearly see this jump of the deviations after the clear cut or the wildfire occurred. In that way allowed us to quantify the effect of the land use change. It also allows, when you use a model and you calibrate it to both periods before and after a land use change, you can start comparing model parameters. And here, because of the considering parameter uncertainty, as probably will come during several talks during the week, we didn't only look at one value, but looked at parameter value distributions, and could show in this case here that there's a clear shift of parameter values from before the wildfire to after the wildfire. So there's an effect on the runoff, as you can quantify by the deviations or model errors. But then you can also learn something about the system and understand why these things happen by looking on how the parameter, the calibrated parameter values change. So for instance, the snowfall correction factor changed clearly. And that is an effect that we have no longer, if the trees are gone, there's much less interception of trees, or interception of snow by the trees. And therefore the sublimation goes down, and that affects the snowfall correction factor. If you want to read more about this kind of idea of how to use models as models for land use change, I refer to this commentary which Ilya van Meerveld and I recently wrote. So, if we want to kind of evaluate models, especially more complex models, we should be critical about our models. And so here I want to make this argument that we not only need to use some benchmarks, and actually we should really think about what we can use as upper and lower benchmarks for our hydrological models. That started from a PhD defense where I was the external evaluator by Liz Lewis in Newcastle. And Liz has applied the Hpv model, so highly complex models, to 300 catchments over the UK, which was a tremendous effort. And in the end, she got this kind of map with different model performances for different catchments in the in the UK. And then our discussion was, well, is this really good? Is it, what does it say, these values? You get sometimes efficiencies of 0.8. That sounds, oh yeah, this sounds really good. But then in some areas here around the London area, there's a much more difficult geology, the efficiencies were less good, so it didn't look so good. So the question was, how to judge it? Is it good or is it bad? So, and that's the discussion led then, or fitted very well to discussions we already had in Zurich about these benchmarks, and it was a very nice test case. The idea here is that because of hydrology oftentimes is very simple, and you oftentimes get a very good model fit regardless what you use. And that is because the simulated runoff is dependent, of course, on what type of model and what type of parameters you use, but it's also very much determined by the type of input data you put into your model, so the precipitation and temperature data. And if you have a highly seasonal rainfall, then your model can't be totally wrong. So it's kind of, regardless how stupid your model is, you won't be totally wrong. So that raises the importance that, well, you should look at what we get really just because of the precipitation pattern determines the runoff, and how much we doing something good because really our model is so good. So let's now go to illustrate that case to the US. We have here a data set of 600 catchments in the US. We calibrated the Hpv model to all of these catchments, and then you see the model performances. And you see that overall, in most of the catchments, we get relatively good fits. Some catchments which are not so good fits, but overall, relatively good fits. Okay. Now the argument, well, but then if you don't have any data, you can't calibrate it. So what do we do in the uncalibrated case? If you don't know anything about it, assume we don't have runoff data. And that was kind of important for this comparison with the Hpv model, where also the case was, well, a physically model we can use uncalibrated. With the Hpv model, we usually rely on calibration. Well, what you can do, what we did here, was to say, well, actually we can run the Hpv model also without any calibration. We just put in random parameters, and we do it not only once, but we do it a few times, so here in this case 1,000 times. So we get an ensemble of model simulations, and then take the average of that. So that is somewhat more robust than just taking one random parameter set. And if you look at that, so this is with random parameter sets, and you get model efficiencies that's very largely. In some areas you get really lousy model efficiencies of 0 or even below, or very clearly very low values. But you see that you also have some catchments where the dots are still orange or red, so where these random parameters give you a really good fit. So that's really important to see. Well, regardless what you use, the weather pattern, the rainfall pattern always ensures a good fit. You get even slightly better fit if you, instead of the random parameters, use national parameters, what we call, so parameter values from some other catchment somewhere in the US, and you again do this ensemble. If you look at these values, you see that up here in the Pacific Northwest, you get model sufficiencies of 0.8, 0.9 without any local calibration. So, which means if you get a model efficiency of 0.7 for some catchment, if you get it for a catchment here, you shouldn't be too proud of yourself. Actually, any kind of model would do that. If you get 0.7 in catchment here in central US, where it's much harder for a model to simulate the runoff correctly, that is more of an achievement. So this illustrates that it's getting a certain model efficiency doesn't mean different things depending on where you are and what kind of, how good the rainfall determines your runoff. So if you're going back to the case in the UK, we have here these different sets, the national parameter sets. So these are parameter sets which have been used in some other catchment, and then using that. We have random. Here's a difference between these two ways to calculate the lower benchmark. And that is, you can argue a little bit what is the better lower benchmark, random or this regional or national parameter sets. The random is very easy to compute. It's no need for other catchment studies, and it's the same for everywhere. With the regional, it's a more challenging benchmark. The choice of parameter ranges from the start with are less important, and it's also a way to avoid unrealistic parameter combinations. Sometimes some parameter value can take different values, but you can't have this parameter value and some other, and these are filtered out by using these calibrated parameters from elsewhere. Anyway, this is kind of, this discussion on what to use as a lower benchmark is kind of still a bit ongoing. What is better? And I think both have their reasons or arguments. But going back to the original question with the Sheetron model in the UK, so how good were these simulations actually? Well, if we look at here we have the sheet models, here we have the upper benchmark, that would be calibrated Hpv model, here we have the lower benchmark, and what you already almost see is that actually the sheet simulations are closer to the lower benchmark than to the upper benchmark. We can look at that more into detail. If we compare the calibrated Hpv model with the Sheetron model, we see that the calibrated Hpv model is better in almost all of the catchments. But that comparison, of course, is a bit unfair because we allow calibration for Hpv and we don't allow it for She. Then we can look at the kind of random lower benchmark, and then we see that about half the catchments are red dots, half are blue dots, so it's half-half whether the She or Hpv is better. Or the She model with a lot of parameters, a lot of efforts to set it up, the Hpv. Let's continue. So now to this question of the value of data. And the question is basically, what should we measure, when and where, and why should we measure something? So if you think of the typical case of a catchment, here, we as hydrologists go into the catchment and we try to measure as much as possible. We put in weirs, we put in groundwater wells, and so on. And typically, the modeler, or we as a modeler, will then come and still say, well, actually, I want to have even more data. We can hardly ever satisfy our models. We always want to have more data. An interesting question, however, is to turn it a little bit around and to say, well, actually, what could be done with less data? And that's basically playing these games of, well, if we would only know part of the things, what would the effect be? And I think as hydrologists, a hydrology community, we should play these games much more in order to provide guidance of what to measure, in which order, why, and where, and what is the first thing we should measure. I guess oftentimes we agree, and if you ask different hydrologists, the first thing we would measure in a catchment is the runoff from the catchment. We put in a gauge. But then when it comes to the second and third thing, opinions vary a lot. Is it soil moisture, groundwater, should be a runoff at some sub-catchment? So there's limited guidance of what to do. Let's give that here. So one question we could ask ourselves is what kind of value do other types of data have? So for instance, water level data. Water level with new technologies, with water level sensors, has become very much simple to observe. So we could throw in one of these water level sensors into the water and get water levels relatively much easier than getting a runoff where we need to establish a rating curve and do a lot of measurements just to get the rating curve, and then have to translate the water levels into flow. So just using the flow, could that be informative? So we did that in a setting with the 600 catchment in the US. So very simple approach here in this case, playing this kind of value for data game. We calibrated the Hpv model once using stream flow and the other time using stream level data. So we assumed that it would only have level data available, even though, of course, we had stream flow available. And having stream flow available allowed us, in both cases, then to evaluate the data against stream flow. So calibrating against something, stream levels, in this case, validating against stream flow. So playing this game, pretending that we know less than we actually do. So just kind of the data set, and the beauty of this data set from the US is that it covers so many climate zones. Usually in Europe, especially coming from a small country like Switzerland, we're very limited in number of climate zones we have. So in Switzerland, we're lacking the dry catchments. If you would, in order to include them for all of Europe, you would go to different borders and different agencies. So this for having a large data set is quite useful here. But then the question comes, well, how do we calibrate against stream level data? Well, the traditional approach would be to establish a rating curve in your model, and then that would require that you at least have 2 or 3 more model parameters to go from the simulated stream flow to a simulated stream level. We wanted to avoid that. We don't want to have any more parameters. So instead, we use the Spearman rank correlation coefficient as a way to calibrate the models against stream level without having any functional relationship, so without defining a rating curve. So what we basically assumed was only that there's a monotonic relationship between stream level and stream flow. So they should go up and down in parallel. But we didn't define any clear kind of any function in that way. So no additional parameter. By doing doing this, looking only on stream level, in theory you could think of, well, you could always have the Spearman rank correlation very high, so things going up and down in parallel, but you always overestimate stream flow by a factor 2. That would give, if you always overestimate stream flow by a factor 2, that would give you a perfect fit. So we were expecting that the fit should not be so good if we calibrate only against level. Well, now here quickly to the results. So this here is calibrated with flow data and then evaluated against flow data. Here is calibrated against level data and evaluated against flow data. And what you can see is that while there's clearly for some catchment it doesn't work so well, they get blue here, whereas they were much better here. For a lot of catchments, the difference is not too big. So the difference down here, for a lot of catchments, the difference between these two calibrations is not too big, regardless of the fact that in theory, the objective function would allow to overestimating your runoff all the time. And then we can do the same here also for validation periods. So here it was calibrated during one period and calibrated for the period and evaluated for the same. Here we have a validation period. Short story, the pattern is more or less basically the same. If we want to get some pattern into that, we can plot the differences against the aridity. So if you plot here we have the difference of the model performance calibrated against flow versus calibrated against level, and then evaluated against flow, against the ratio between precipitation and potential evaporation. And what you see is that for dry catchment on this side, you can have rather large differences. But for wet catchments, for humid catchments, differences become much smaller. So if we put in here the running mean as lines, you see that they get quickly down, and differences are relatively small for the more humid catchments. The explanation here simply is that if you have a lot of rainfall, then on the humid catchment, the total volume of runoff is very much determined by the volume of rainfall. So you can't go too wrong. So this idea of overestimating your flow all the time by factor 2, it's just not possible out of water balance constraints. In dry catchments, on the other side, that is possible. If you have the wrong soil parameters, you might always overestimate or always underestimate your runoff. So there the stream flow alone is not enough, but in wet catchments it is already very informative. We can present the data here also in a Bodico space where you have the energy, so you know this Bodico curve with an energy limited region and a water limited region, and you plot the potential evaporation divided by precipitation against the actual evaporation divided by precipitation. And now the color code gives the difference of the model calibration. Blue, again, small differences, red, larger differences. And you see this clearly divide in the energy limited space. It is model performances, or the water level is already informative. In the water limited space, it's more the differences can be quite large. And here it's the same as before, now just only color-coded, the evaporation ratio, actual evaporation divided by potential evaporation, and that allows to see some of the differences down here where you have some evaporation, catchments where evaporation plays a larger role than in other catchments, and you see the effects of that on the model performances. So in general, the more potential evaporation is reduced, the worse, the more of a difference it is. And that is when the soil routine in the Hpv model becomes very important. So controlling how much water actually leaves the catchments. Now between these two figures, so here calibrate only against stream levels. Here we calibrate against stream levels and some volume error, where you basically say, well, we know the mean runoff. You assume that you know the mean runoff of catchment, and you know that from some kind of regionalized values, neighboring catchment or so. And what you see is that kind of if you go back and forth between the two, you see that all the points especially for dry catchments come down. So by adding this kind of one information, you can improve your model quite a lot already. You can put that in the other way, the difference by calibrating against only level and then calibrating with level and the volume error. And you see that for those catchments which were worse, where the difference was largest, you get some kind of improvement. About half of the error is gone by adding this one piece of information. So that means now if we could kind of get some good estimate of the volume error, that is could help to improve the stream level calibrations. Okay, I want to end with here is kind of going now the value of data going into a different field, namely into the field of citizen science, which is a new kind of field where we are trying to use new types of data which are collected. And again, the value of data is a very central question. Just very briefly for citizen science, we want to engage the public, we want to get different people to, not only scientists to collect data, but also the kind of interested public. And there have been some examples, very successful examples in the fields of bird watching or plants reporting. They have been running for decades, sometimes even in terms of bird watching for hundreds of years, 100 years. Recently, they started some projects on citizen science in hydrology also. The Crowd Hydrology project from the US is one example. The Resensit from Europe, where Dimitri is also involved, is another example. And just to give an example of how this crowd hydrology looks like. So basically the idea of crowd hydrology is they put this stage into the stream, they have the phone number here, and they ask you to text, if you pass by, you should read the value and you should text it to some central database. This here is the map of different stations which are located in the US, mainly in the northeast, some in the northwest. And one of these two stations I recently visited during sabbatical in Oregon, where I took this kind of, it was a sign, and I read the value and I texted it. And this is the data, so data here has been collected. The last point is my point, before hundreds of points from different volunteers. And this kind of shows two things. One is actually people are willing to contribute, not everyone, but enough people to get some data series. But it also shows the kind of some of the issues with data. Some value is totally wrong, there's some noise or some uncertainties. The data is not fully so sure as we sometimes are used to. And so we started then 2 years ago in Zurich this project which we call groundwater. And basically groundwater is, we have two different approaches, two different questions. One is what can be observed and how can that be observed? So the more technicalities, how good are people at observing things? How can we support people to collect data? And smartphones play an important role there. And also the question is, of course, what accuracy is that we can observe. And then the other side, which is a more modeling side, is the value of data. Well, if we would have that data, how valuable would it be? So playing, again, this kind of games of what, if the data would be really uncertain, would that still be useful? And what types of data would be most useful? And just as an example, how we're, well, an important thing here, our vision is to have a scalable approach. Crowd hydrology is great with these stuff gauges, but it's limited that they need to install the stuff gauges everywhere. So that means not everyone can easily set up a site. So what we want to have is an approach where people themselves can easily set up somewhere without any physical installation, which means it's like a geocaching approach where it's scalable. So if there are 100 times as many people, then it would have also 100 times as many stations been possible. Okay, so one way of things what we are doing here is, for instance, kind of quantifying how good or bad are people at estimating stream flow. So we went out a number of times to different stream locations for different size streams in Switzerland and asked random people on the street how much is flowing in the stream. And as you might guess, the estimates vary quite a lot. They probably would vary quite a lot if I would take you out to the next stream. Even if you're educated hydrologist, you would have kind of, our estimating stream flow is quite hard without any gauging. But they were kind of sometimes not too wrong, especially after some kind of explanation once we explained to people. Well, so we first asked them and then we gave them a short introduction how you should estimate it. So typical, take the width, take the depths, flow velocities, estimate that, and typical velocities are in a certain range. After that, the outliers disappeared a little bit, and interestingly, there is this kind of wisdom of the crowd. If you take the average of all the estimates we run, it was surprisingly close. Still, there's a large variation, and if you look from that variation, we're then able to calculate the error distribution, so which was kind of here defining kind of normalized for all the different estimates. We summarize those and we're able to calculate the kind of error distribution, which allows us to quantify how, if you have a single observation, how bad or wrong would it be. Okay, so with that in mind, we then can assume, say, well, how valuable would such data be? So we know it's highly uncertain, and it's spotty in time because a citizen would do it every day, but would maybe come there on the weekend, or maybe only in summertime, only once a week, and so on. So we generated this different time series of from the observation. We took real observations and then modified the observation data to make it look like citizen science data. So we added an error and we made it more spotty in time, so having only a few data points. And then we calibrated the model. Again, we were using an upper benchmark, calibrating the model with a full data set. We were then assuming no errors. And of course, the model was, with no errors, the calibration with only limited data was not resulting in the same performance as a full calibration, but it was not too bad. Kind of model relatively achieved 80% of the model performance with just 12 values or just a weekly value. Okay, but then also we had introduced this lower benchmark, the random parameter set. So if you would use random parameters, you would get for different catchment a certain variation, but you would also already come in. That's kind of important to say how far you would come, and with the but definitely if there's no errors, then even the 12 points or 50 points or monthly observations would have already been an improvement for your modeling compared to the random case. Okay, but now with adding the error to that, what we found here is if you have limited data, like only 12 values for a year or only only weekly values, basically together with this error, we end up in the same range as the random parameter sets. So basically meaning if the error is so large, we don't gain anything. We played then the same game with taking the error of 50% and 25%, and it turned out that by 50 or at least by 25%, if you could reduce the error, then the data would become informative. So again, this is kind of a way to say how much effort is needed to make the data valuable. So we can play these games, and now we can think, well, is there anything we could do to improve the people's estimate of the stream flow? Should we change? What could be changed? Can the education, explanation be changed? Or is it simply not possible to achieve this reduction? So these kind of playing these games is kind of very important to guide, especially citizen science approaches, of where to put the effort. Of course, it became very clear that, well, stream flow might be very hard to estimate. So what about stream level? Couldn't we observe stream level? And previously we showed stream level is really informative. But now again, with stream level, if it's high resolution. But if you want to have a scalable approach without any physical installations, we can't really have this water level on the centimeter, but it might be possible to have water level classes. So for instance, the water level is above or below a certain rock in the stream. So what we again played this game, transformed our observed data into pretended data. Taking the stream flow into stream level classes down here, and then using this data to calibrate the model. And this is the type of data that would be possible to observe with in a citizen science approach. So you go to the stream, you have and the idea here is to have a kind of virtual stuff gauge, which you take a photo and you put in your stuff gauge, and then you can observe stream level classes. Just to illustrate a little bit, so you come to a place, your favorite stream, you have your location, you take a photo and put in this stuff gauge. So take a photo, put in a stuff gauge, you size it, you then move it so that it's at the 0 level. And then next time you come out to your site, you realize, you take the photo, and it might not be fully visible here, but you then can think, oh yeah, this rock is now not visible anymore, so that must be a different. Now we have a different water level class. So this kind of photo with this virtual stuff gauge allows to get water level classes. So with the smartphone app, we kind of collect now these water level classes. But now again, it comes to the question about water level classes. Is this really informative? And we played the same game here, running the model with assuming that we only would have water level classes, long time series. And the results are summarized in this not so easy plot. Just quickly run you through. We have the upper benchmark, calibration against all stream flow data. We have the lower benchmark, calibration against random, no calibration, so random parameters. Then we have the calibration against the high resolution stream levels. So that was what I showed you before in the study on stream levels. And in between we have calibration against stream level classes. And what you can see here is that 2 stream level classes are already informative, so you get better, on average, better fits than just with random parameters. And then this increases for 3, 4, up to 5, 6 classes, and after that it almost levels. And that again, that is kind of very good news for citizen science projects, because 3 to 5 classes is something we think people can identify in the stream. If you pass by the stream, you can see, well, now it's over this rock. Yesterday it was below, so you can get this time series of stream level classes. And so we launched this smartphone app some 1.5 years ago, and beginning more carefully, and now more distributed much more, especially in Switzerland. And stations are popping up in different parts in Switzerland, but also worldwide. The app is using OpenStreetMaps, so basically it can be used everywhere around the globe. And of course, I hope to see a few stations in Moscow and other parts of Russia soon popping up. It looks like this here. People go to the station, take different pictures, different levels, and we get this time series of stream level classes, so which almost looks like a hydrograph. And this is really informative for model calibration. Just to make you more curious about the app, hopefully, we have not only stream level classes, we also have categories to observe soil moisture, again with a qualitative scale you can see water on the ground to the driest. You can sit on the ground and you won't get wet, and the next driest is then you would sit on the ground, but after a while you would get wet. And we have observed temporary streams where you go from water flowing to no water at all, and then there's standing water, and then also kind of trickling water and different water pools. So these 3 variables, water levels, soil moisture, and temporary streams, is something we think people can provide information to, and we're now kind of launching this app to collect this data. I have here a screenshot from the German version. Of course, there's also the English version, as there's a French and a Spanish version. And if any of you is interested in translating it to a Russian version, we would be very delighted to provide you with the files. So to summarize this morning here, what I kind of take-home messages here: simple models can be useful. That's very much a continuation of the first talk today. There is a value for these simple models, even if we have more complex models, but sometimes we need these complex models for different reasons, but in a lot of applications, simple models still have their value. And my important message here: use lower and upper benchmarks, especially the lower benchmark. Quantify how good your model, quantify how good you would get just because of the climate or meteorological conditions. Simple approaches, like I just presented with the groundwater project, can provide useful data, potentially useful data. And the value of data in such projects or in general can be evaluated. So let's play these games, take whale data and pretend that we have less data in order to provide some guidance of what we should measure and how we should measure that. And what was, at least to us when we started this work, was surprising that the water level observations can already be very informative because they provide the timing and some information, important information. So the final thing is only just go and get the app and install the app and collect some data, and I really would be delighted to see some stations in Russia popping up. I think so far we don't have so many here. I have the references. I can distribute the slides later on. So here are some references on papers which have influenced what I'm doing, and also some of our studies which I've talked about today. But I'm finished here, and I would be happy to take some questions if you have any before going for lunch.